right, welcome to lesson 6 on acceleration. So lesson 5 and 6, kind of two shorter lessons. I just wanted to kind of break up so that it doesn't get too confusing with all the different types of things going on. So in this one, we'll learn about acceleration and the two learning objectives. They're identical except for one word. So first, we're going to represent motion with constant velocity. We did this in the previous lesson with position versus time graphs, but now we're going to represent it with velocity versus time graphs, and of course, mathematically. Okay, so it's the difference between position versus time graphs and velocity versus time graphs. And constant velocity looks different on those different types of graphs. And then we'll do the same thing with changing velocity and looking at that on a velocity versus time graph and also mathematically. So, so here I have a position versus time graph, x versus t. And when we say it's an object that's moving, and can we figure out what the velocity is? Well, we learned in the previous lesson that it's just the slope. Okay, so if we were to find the velocity, the average velocity or constant velocity during this 2-second time interval, it would be the displacement, right, the final minus the initial. All right, so that would be minus 3 minus 0 over time is 2 minus 0. Okay, so notice that gives us minus 3 halves or minus 1.5. And I didn't put any units here, but maybe they're meters per second. Okay, so it's really important to do the final position minus the initial position, okay, because that helps us define it as a velocity. So we know that since it's sloping down, it's a negative velocity. So negative velocity, sometimes we might think, oh, that means we're slowing down. No, it doesn't. It just means negative velocity is just telling us direction. It means that it's moving at a certain velocity, but in a direction that we define as being negative. So maybe this could be an object moving on a number line. And wherever we define the 0, if we go to one side of the 0, we're moving in the negative direction. If we're moving to the other side of the 0, we're moving in the positive direction. And so then we know too from the previous lesson, this is just going to be 0. And then since this is going up, now this is going to be a positive velocity. And so I'm going to show you a little demonstration here with the iOLAB device. And you're going to do something similar in your lab. And so we're going to actually make this graph with the iOLAB device. And what's nice about the iOLAB software is that it will automatically create the velocity versus time graph. So we could see what that corresponding graph is going to look like. And so it's a big part of the homework. It's a big part of the lab. And it's going to be a big part of the midterm too. So it's something you want to keep an eye on. So let's look at this video then. Okay, so here we can see I have the iOLAB device on a table, and I've got the wheel sensor checked off. And under wheel, you can choose position, velocity, and acceleration. And it will map position versus time, which is what's showing here. It'll also show, you could see a velocity versus time graph if you check that one off. And then an acceleration versus time if you check that one off. So I'm just going to have position versus time first, and we'll see what happens. I'm going to show you how I make that graph. Yeah, so it's essentially the same graph, except the other graph that I had a drawing of, it actually goes, this would go up further, but you can see that, right? This wasn't necessarily slowing down, right? It just meant that the device was moving in the left to the left. So the negative here is telling us left. Okay, and when you get your device, you'll actually see that there's a coordinate plane on there, and you can see what's defined as positive and negative directions. And so then going this way, pretty much the same velocity I did here, but it just was showing that it was moving in the opposite direction. Okay, and then by seeing that it started at 0 and I ended up essentially back at 0, we could tell that pretty much where it started is where it ended up. So I brought it back to exactly where it was. All right, so now I'm going to check off the velocity versus time. And what do we see here? All right, well, we see real life. It's kind of messy. And so I'm going to highlight the portion where it's the straightest. Okay, so that's the first portion where it's essentially a straight, right? We could see the reality of the curve there, right? We didn't see that in the uniform motion model. We just went from to right? So straight to straight. So I tried to highlight part of it here, and you could tell that, can I move this? Yes. You could tell that I didn't quite get it perfect because, right, this is the curving here, corresponds to the curving here. But you see where it's mostly straight here. What do you notice down here? It's a little bumpy, but it's essentially a flat line, right? It's a flat line. Okay, so on a velocity versus time graph, well, what do we see? We see that there's, at a constant velocity, it's a flat line. Okay, so on position versus time graph, flat line meant at rest, which in a way is constant velocity. But what is the axis measuring on a velocity versus time graph? The y-axis is measuring velocity. So if it's constant, then constant velocity, then it ought to be a flat line. Okay. And I pre-recorded this, so all right, then what do I do? All right, so then I highlight the flat part, oops, and we can see they're both flat, right? But the difference here is on the position time graph, it's flat at -6. So where I stopped the device momentarily was 0.6 meters to the left of where it started. So it's flat there at 0.6. It's staying at that 0.6 meter mark. Whereas on the velocity time graph, it's flat at 0 because it's at rest. So the velocity is 0 at that point. Okay, and then we notice here that when it's going back to its original position, now we see that we have a positive velocity. Okay, because it's moving back toward the positive direction. Okay, so this is tricky. Take some practice. That's the point of Lab 1, is to actually get a feel for this and practice it. So even if you're working with a partner or a group on this, I really can't stress enough how important it is for you to physically try moving the device yourself. It's going to make me trying to tell it to you is going to be nothing compared to you actually physically doing it. It's that kinesthetic touch that's going to your brain that's really going to help you understand how these graphs work. And that's going to give you the best way to understand them. So please take advantage of that. That's a big part of why we do lab in physics anyway, in physics courses. So it's a little tricky, but I think you'll start to get to understand how these are working. Okay, because as you might be thinking, well, why isn't this still negative down here? Because the position's still negative. Well, it has nothing to do with that. It really has to do with the slope. Okay, so the slope, right, is a positive slope. Okay, so a positive velocity. Here it's a negative slope, so negative velocity. Okay, so let's take a quick look at a question here. So I have a position versus time graph and several velocity versus time graphs. So if you want to take a moment to think about which is the corresponding one. So just think about that. I'll give you a minute to think about that. Okay, now that you're done fast forwarding through that, pause. I guess what I could do is I should just tell you to try to pause the video at that time to think about it, then you can pause for as long as you want. Okay, so it's C. Okay, a little pretty tricky. All right, but we know here at this portion, we're at a constant velocity. It's a positive slope. So that means the velocity, although it's, it starts off at a negative position, it's moving in the positive direction. So that means it's a positive velocity, a positive constant velocity. And then we see it curves down to basically a flat line. So at the end, it's going to be at rest. So at the end, it's at rest there. And then we could see in this portion in between, it's slowing down. So it's a little tricky. So that's a pretty tough one to think about. So if you didn't get it right the first time, that's quite all right. You'll do a much better job after having done some of these homework problems and the lab as well. So how do we tell velocity from a velocity versus time graph? What is the slope? All right, so we tell velocity just by looking at, well, where is the number on the y-axis, right? Because that axis represents velocity. So that's just how we find velocity. Pretty simple. Just like on the position time graph, we look to find the displacement or position. We just looked at the position axis. So what does the slope tell us? Well, remember, slope is rise over run. And so what's rise here going to be? Well, it's going to be delta V. And the run's also, again, going to be delta T. Well, when we have a change in velocity over a time interval, that's what we call acceleration. So the slope of velocity of a velocity versus time graph is acceleration. And we symbolize that with a lowercase a. And so similar to how we call the position versus time graph, sometimes we refer to it as a velocity graph. Well, we can also refer to a velocity time graphs, if we want, as acceleration graphs. So the slope tells us acceleration. And what are the units? Just use a different color for units. Well, we see velocity. We usually typically, the SI units anyway, are meters per second. And time, we measure SI units in seconds. So this is literally equivalent to a meter per second per second. It might sound a little weird, but that's a totally perfectly legitimate unit to use. More often, the way we say it in physics is meters per second squared is how we usually refer to acceleration, the units of acceleration. Okay, so what does constant velocity look like on a velocity versus time graph? Well, like we've been saying, it's just a nice flat line. Okay. What about this flat line in the middle picture? It's flat. I mean, it's straight, but it's not flat, but it's still straight. So what is that telling us? Well, we know the slope is acceleration. The fact that it is a nice straight line, right? On a position time graph, that straight line was constant velocity. Well, here it's going to be constant acceleration. And then what about if we have a curved line? Well, you remember on the position versus time graph, we had a curved line that was changing velocity. Well, this is also a changing velocity, but because it's curving, right, it's not a straight line, it's not a constant acceleration. Now it's a changing acceleration. And just like in position versus time graphs, well, we really can't analyze that using slope because we now have we now have to deal with calculus again. So I'll show you in a couple slides how we do that. All right, so analyzing these graphs is we get some interesting, we make some interesting connections. So if we were to say find the area under the curve of this graph, right? So this area under the curve, well, what might that be? What is that? What information will that tell us? Well, we know area is what? Length times width, or yeah, length times width. So it's essentially, this is the width. That's what? That's the change in velocity. All right, so area is change in velocity, length or width, times what? The length. Right, which is the time interval. What is change in velocity times change in time? Isn't that displacement? Right, so we can look at the velocity equation, right? Is position or displacement over time interval. Well, if we just put that delta t over there, right? Delta v delta t is delta x. So it's a useful thing to know, and it will also help us to model constant acceleration. So if we were, say, given an initial position, then if the displacement is the velocity, well, in this case, it's constant, so I just put v delta t. Well, we can also say, displacement is final position minus initial, right? And so if we knew what was the initial position, then we could find the final position. Okay, so we did this in the previous lesson. All right, so let's try an example of this then. So let's say that we have a graph here, and going along with the graph, Daisy starts from a position of +5 meters and walks with a constant velocity as shown on the graph. So what is her position at t = 6 seconds? So she's moving with a constant velocity. We can read that from the graph, 4. I should have put units, but let's just say the units are meters and seconds. Okay, her initial position is plus 5 meters. And what is her position at 6 seconds? Okay, so if she starts, so starts is 0, end time is 6, so then our delta t, our time interval is 6 seconds. Okay, so we know from the area, displacement is velocity times time interval. Okay. And we also know that that's displacement is x final minus x initial. And what are we looking for? We're looking for what's her position at 6 seconds. So if we solve for final position, we know her initial position is plus 5 meters. Her velocity is constant at 4 meters per second. And she's moving at that constant velocity for 6 seconds. All right, so then we got 5 plus 4 times 6, 24. So that's 29 meters. So she will have been at a position of 29 meters then. Okay, and so again, we had an initial position of 5. That's the first part. And then her displacement, right, is this area, length times width. Cool, right? I know it's not cool. I think it's cool. They're models. These are all things we make up to understand things. So, right. So what if we have? So that was a constant velocity. What if we have a constant acceleration? Right. Well, we could still get the area under the curve. Now, though, area of this is not length times width, right? Well, it's basically a triangle. So area, right, is like the half base times height. Okay, so area, right, we do triangle, 1/2 base times height, and so the displacement is 1/2. All right, well, so what do we have? Base times height. So we have change in v and change in t. So this is not constant velocity anymore. And maybe we can say, well, we can say v final minus v initial. All right, so I'm not going to do example of this yet because I want to wait till the next lesson when we really dig into constant acceleration, and we'll apply this a bit more and do some more examples. But this lesson, I just want you getting you used to velocity versus time graphs, and what does it look like, the difference between constant velocity and constant or changing velocity, which is constant acceleration. So I'm just trying to take off little bites here and build up to the harder stuff. All right, so then what about the area under the curve when we have this situation? Okay, a lot messier, can't just do it with nice algebra. So there's no specific shape. So we need to use calculus. So So you've seen this in your books before. All these rectangles, right? And then we add up those smaller, make those change in the change in time, the delta t smaller and smaller and smaller. So those rectangles get skinnier and skinnier and skinnier, and the skinnier they get more accurate they get, right? And again, it's a limit. So the position, right, is the limit as the time interval approaches 0. And then we're gonna have a sum, right? We're gonna have a sum of all those velocity times time intervals. Okay, the change of all those rectangles, right? So if they're rectangles, I'll just do one. Right, it's going to be a change of velocity times a change in time. Okay, and then when we do a sum in calculus, if you haven't gotten to Calc 2 yet, well, we call this a sum is essentially an integral. That's all an integral really is a sum, right? So from t initial to t final of the velocity times, or I guess we call that dt, not delta t anymore. Okay, so we're not going to do these integrals, but we're just making these connections. We know a lot of you are just freshmen, just starting out, so you don't. Some of you haven't taken Calc 2 yet. So the prerequisite for this course is, or it's a co-requisite, is Calc 1. So we don't expect you to know any calculus for this course. So, but the point is to try to make these connections of how calculus fits in and is related. Okay, so Isaac Newton invented calculus in order to try to explain motion, to try to explain all this mechanics of everything going on. So, there's a big connection there. But again, he's very deep into physics. So you're just starting out. So we're not gonna bury you in all this. All right, so now you should be able to finish that first, that one problem where I said in the end of the last lesson that you might not be able to finish it because it expects you to know what area under the curve is. Now you know, and now you can do a few more problems here from homework 2. So did you learn to represent motion with constant velocity using these velocity time graphs and math? Well, we know what constant velocity looks like on a velocity versus time graph. It's just a flat line. And we're able to mathematically determine some things. We could find out how far something's going to be from after it's moving a certain amount of time at that constant velocity. And then we learned about changing velocity now. So when we change at a constant rate, right, nice and easy to work with. We the area, right, is just a half base times height. So that's also called constant acceleration. And then when we have this changing acceleration, that's where the integral comes in. All right, so that's it for lesson 6.